What if you could take everything that's great about TIG welding and make it even more powerful, more precise, more stable, capable of producing deeper weld penetration, and powerful enough to weld everything from razor-thin medical components to critical aerospace parts with incredible accuracy? That's exactly what plasma arc welding was designed to do. At first glance, plasma arc welding, or PAW, looks very similar to TIG welding. Both use a tungsten electrode, both use shielding gases. Both can create exceptionally clean welds. But beneath the surface, plasma arc welding operates on an entirely different level. Instead of allowing the arc to spread naturally, PAW squeezes the arc through a tiny nozzle, transforming it into an intensely concentrated plasma jet capable of reaching astonishing temperatures. The result is a welding process that delivers incredible precision, superior arc stability, and penetration levels that traditional TIG welding often struggles to achieve. That's why industries such as aerospace, medical device manufacturing, electronics, turbine production, and precision tube manufacturing rely on plasma arc welding when quality simply cannot be compromised. But what exactly is plasma? How does a welding arc become a plasma jet? Why does plasma arc welding create deeper penetration than TIG welding? And what makes this advanced welding process one of the most precise joining methods available today? In this video, we'll break down everything you need to know about plasma arc welding, including how it works, its major components, operating modes, applications, advantages, disadvantages, and how it compares to TIG welding. By the end of this video, you'll understand why many engineers consider plasma arc welding one of the most sophisticated arc welding technologies ever developed. Let's get started. What is plasma arc welding? Plasma arc welding, commonly known as PAW, is an advanced arc welding process that uses a non-consumable tungsten electrode to create an extremely concentrated and stable welding arc. The process is closely related to TIG welding, but with one major difference. In TIG welding, the arc is relatively open and shielded by inert gas. In plasma arc welding, the arc is forced through a specially designed nozzle that constricts and compresses it. Think of it this way. Imagine water flowing from a garden hose. The water comes out smoothly. Now, place your thumb partially over the opening. The water suddenly becomes faster, more concentrated, and more powerful. That's essentially what happens inside a plasma welding torch. The welding arc is compressed into a narrow, high-energy plasma beam. This increases arc temperature, arc pressure, arc stability, and penetration capability. As a result, plasma arc welding can create highly precise welds with excellent control and consistency.
What is plasma? Before we go further, let's understand the term plasma. Most people are familiar with three states of matter: solid, liquid, gas. Plasma is often called the fourth state of matter. When a gas is heated to extremely high temperatures, its atoms become energized and release electrons. This creates a mixture of positively charged ions and free electrons. That ionized gas becomes plasma. In plasma arc welding, this plasma becomes the primary source of heat used to melt and join metals. Because plasma can carry enormous amounts of energy, it creates a very intense and focused heat source. Why was plasma arc welding developed? Engineers developed PAW to overcome some limitations of traditional TIG welding. TIG welding is known for producing clean and high-quality welds. However, it has limitations when it comes to arc stability at very low currents, deep penetration, and high-speed welding applications. Plasma arc welding solved many of these issues by creating a more concentrated arc. This improved weld consistency, productivity, precision, and control. The result was a process capable of handling both microscopic welds and heavy industrial applications. Where is plasma arc welding used? One of the most impressive aspects of PAW is its versatility. The process can weld extremely thin materials while also handling thicker sections with remarkable efficiency. Let's explore some of its most common applications. Aerospace industry. Aircraft and spacecraft components require extremely reliable welds. Even a small defect can compromise safety. Because plasma arc welding produces highly controlled and repeatable results, it is widely used in aerospace manufacturing. The deep penetration and narrow heat-affected zone make it particularly attractive for critical applications. Medical device manufacturing. Many medical devices contain tiny precision components. Traditional welding methods may introduce too much heat or distortion. PAW's low current capabilities allow manufacturers to weld delicate parts with exceptional accuracy. This makes it ideal for surgical instruments, medical implants, and precision tubing.
Electronics industry. Electronic components often require extremely small and accurate welds. Microplasma welding allows manufacturers to join miniature parts without damaging surrounding components. Steel tube manufacturing. One area where plasma arc welding truly shines is tube production. Its ability to perform high-speed continuous welding makes it highly efficient for manufacturing stainless steel tubes. Marine industry. Shipbuilders and marine fabricators use PAW when welding corrosion-resistant materials such as stainless steel. The process produces strong welds capable of withstanding harsh marine environments. Turbine blade repair. Turbine blades are expensive and highly engineered components. PAW allows technicians to repair and rebuild damaged areas with exceptional precision. This can significantly extend component life. Tool and die repair. Manufacturing facilities frequently use PAW to repair worn or damaged tools and dies. The concentrated heat allows repairs with minimal distortion. Major components of a plasma arc welding system. Now let's look at the equipment that makes plasma arc welding possible. Number 1. Power supply. The power supply provides the electrical energy needed to create the arc. Like TIG welding, PAW typically uses a high-quality DC power source. The system must provide stable current to maintain consistent arc performance. Number 2. Tungsten electrode. The tungsten electrode is non-consumable. Its job is to carry electrical current and generate the arc. Because tungsten has an extremely high melting temperature, it can withstand the intense heat generated during welding. Unlike consumable electrodes, it does not become part of the weld. Number 3. Plasma welding torch. The torch is the heart of the entire process. This is where plasma arc welding differs dramatically from TIG welding. Inside the torch is a specially designed constricting nozzle. This nozzle squeezes the arc into a narrow plasma jet. The compressed arc becomes hotter, more focused, and more stable. This is the key to PAW's superior performance. Number 4. Water cooling system. The plasma torch operates at extremely high temperatures. Without cooling, the nozzle would quickly become damaged. That's why plasma arc welding torches are always water-cooled. A water recirculation system continuously removes heat from the torch. This protects critical components and extends equipment life.
5. Plasma gas supply. Plasma gas is responsible for creating the plasma jet. Common gases include argon, helium, and hydrogen mixtures. The gas passes through the constricting nozzle and becomes ionized into plasma. 6. Shielding gas supply. A separate shielding gas surrounds the weld area. Its purpose is to protect the molten weld pool from atmospheric contamination. This separation between plasma gas and shielding gas is one of the defining characteristics of PAW. 7. High-frequency generator. A high-frequency generator helps initiate the arc. This allows the process to start smoothly without damaging the electrode. How does plasma arc welding work?
Now, let's walk through the welding process step by step. Step 1. Arc initiation. The process begins when electrical current flows to the tungsten electrode. A high-frequency generator helps establish the arc. The arc forms between the electrode and either the nozzle or the workpiece. Step 2. Plasma formation. As plasma gas flows through the torch, the arc ionizes the gas. The gas becomes electrically conductive plasma. This plasma contains enormous thermal energy. Step 3. Arc constriction. The plasma passes through a narrow nozzle opening. This compresses the arc dramatically. This concentrated energy is what gives PAW its exceptional penetration capability. Step 4. Shielding gas protection. At the same time, a separate shielding gas surrounds the plasma jet. This protects the molten weld pool from oxygen, nitrogen, and moisture. Without this protection, weld quality would suffer significantly. Step 5. Metal melting. The plasma jet strikes the workpiece. Its concentrated energy melts the base metal rapidly. Depending on the application, filler metal may or may not be added. One major advantage of PAW is that filler metal remains optional. Step 6. Welds formation. As the torch travels along the joint, molten metal solidifies behind it. The result is a strong, precise weld with excellent penetration and minimal distortion. Transferred arc versus non-transferred arc. Plasma arc welding can operate in two different configurations. Non-transferred arc. In this mode, the arc forms between the tungsten electrode and the torch nozzle. The plasma jet exits the torch and transfers heat indirectly to the workpiece. This is commonly used for specialized applications.
Transferred arc. In transferred arc, the arc forms directly between the electrode and the workpiece. This provides maximum heat transfer and is commonly used for welding operations. Most industrial PAW applications utilize transferred arcs. Plasma arc welding versus TIG welding. Since PAW evolved from TIG welding, comparisons are inevitable. Let's look at the differences. TIG welding. Simpler equipment, lower equipment cost, easier to learn, less maintenance. Plasma arc welding. Greater arc stability, deeper penetration, higher precision, better standoff tolerance, faster welding speeds, smaller heat-affected zone. In simple terms, TIG welding is often preferred for general-purpose work, while PAW is chosen when maximum precision and performance are required. Advantages of plasma arc welding. Now let's examine the benefits that make PAW so attractive. Exceptional precision. The concentrated plasma beam allows highly accurate weld placement. Deep penetration. The compressed arc delivers more energy into a smaller area. This results in superior penetration. Stable arc. PAW maintains excellent arc stability across a wide current range.
High-speed welding. The concentrated heat source allows faster travel speeds. Smaller heat-affected zone. Less surrounding material is affected by heat. This helps reduce distortion. Suitable for thin and thick materials. Few welding processes offer such versatility. Disadvantages of plasma arc welding. Despite its impressive capabilities, PAW does have limitations. High equipment cost. Plasma welding equipment is considerably more expensive than standard TIG setups. Complex operation. Operators require additional training to fully utilize the process. Higher maintenance requirements. The torch design is more sophisticated and sensitive. Bulky torch design. The water-cooled torch can be larger and heavier than TIG torches. Increased noise. The high-velocity plasma jet generates significant noise during operation. Radiation exposure.
The process produces intense ultraviolet and infrared radiation, requiring proper protection. Conclusion: Plasma arc welding represents one of the most advanced forms of arc welding available today. By taking a conventional TIG-style arc and compressing it through a specially designed nozzle, PAW creates a high-energy plasma jet capable of delivering exceptional precision, deep penetration, and remarkable arc stability. From medical devices and electronics to aerospace components and steel tube manufacturing, plasma arc welding continues to prove its value wherever quality and precision matter most. And now, the next time you hear the term plasma arc welding, you'll know that it's far more than just another welding process. It's a highly engineered technology designed to push welding precision to an entirely new level. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications for more deep dives into welding technologies, fabrication techniques, and industrial engineering. Thanks for watching, and we'll see you in the next video.